Dear learners, in this session we will be discussing about phosphorus and its compounds. After this discussion, you will be able to differentiate allotropic forms of phosphorus, describe the method of preparation, properties and uses of phosphine, explain the structure, preparation and properties of phosphorus halides, explain oxo acids of phosphorus. Phosphorus is found in many allotropic forms. The important ones being white, red and black phosphorus. White phosphorus is more reactive than red phosphorus. This is due to more angular strain in its structure. It is made up of P4 units. It is a translucent, white, waxy solid. It is poisonous, insoluble in water, but soluble in carbon disulfide. White phosphorus glows in dark. This is called chemiluminescence. It dissolves in boiling sodium hydroxide solution. In an inert atmosphere of carbon dioxide, giving phosphine, that is pH3. It readily catches fire in air to give dense white fumes of P4O10. Red phosphorus is obtained by heating white phosphorus at 573 Kelvin temperature in an inert atmosphere for several days. It is odorless, non-poisonous and insoluble in water as well as in carbon disulfide. Chemically, red phosphorus is much less reactive than white phosphorus. It does not glow in the dark. Black phosphorus has two forms, alpha black phosphorus and beta black phosphorus. Alpha black phosphorus is formed by heating red phosphorus in a sealed tube at 803 Kelvin temperature. It has opaque, monoclinic or rhombohedral crystals. It does not oxidize in air. Beta black phosphorus is prepared by heating white phosphorus at 473 Kelvin temperature and under high pressure. It does not burn in air up to 673 Kelvin temperature. Now, we will discuss about phosphine. This is an important compound of phosphorus. It is a colorless gas with rotten fish smell and is highly poisonous. Phosphine is prepared by the reaction of calcium phosphide with water or with dilute hydrochloric acid. In the laboratory, it can be prepared by heating white phosphorus with concentrated sodium hydroxide solution in an inert atmosphere of carbon dioxide. Pure phosphine is non-inflammable, but it becomes inflammable owing to the presence of P2H4 or P4 vapors. Phosphine is purified from impurities by absorbing in hydroiodic acid to form phosphonium iodide, that is PH4I, which on treating with potassium hydroxide gives off phosphine. Phosphine is slightly soluble in water, but its solubility is very less than solubility of ammonia because there is no hydrogen bond formation between phosphine and water molecules. The solution of phosphine in water decomposes in presence of light, giving red phosphorus and hydrogen. When absorbed in copper sulphate or mercuric chloride solution, the corresponding phosphides are obtained. Phosphine is weakly basic and like ammonia gives phosphonium compounds when reacted with acids. Have you ever thought why bond angle in phosphonium ion PH4 plus is higher than that in phosphine? As you can see in figure, there should be lone pair bond pair repulsion in phosphine, which is absent in phosphonium ion. This lone pair-bond pair repulsion brings pH bonds closer and this decreases H-pH bond angle. What are the uses of phosphine? The spontaneous combustion of phosphine is technically used in home signals. Containers containing calcium carbide and calcium phosphide are pierced and thrown in sea when the gases evolved, burn and serve as signals. It is also used in smoke screens. Now, let us discuss halides of phosphorus. Phosphorus forms two types of halides, phosphorus trihalide and phosphorus pentahalide. For example, phosphorus trichloride and phosphorus pentachloride. Phosphorus trichloride has pyramidal shape and phosphorus pentachloride is trigonal bipyramidal. Phosphorus trichloride is obtained by passing dry chlorine over heated white phosphorus. It is also obtained by action of thionyl chloride with white phosphorus. It is a colorless, oily liquid and hydrolyzes in the presence of moisture. It reacts with organic compounds containing hydroxyl group in them. For example, ethanoic acid, ethanol. Have you ever thought, why does phosphorus trichloride fume in moisture? It is because phosphorus trichloride hydrolyzes in the presence of moisture and give fumes of hydrogen chloride gas. Coming to phosphorus pentachloride, it can be prepared by reaction of white phosphorus with excess of dry chlorine. It can also be prepared by the action of SO2Cl2 on phosphorus. Phosphorus pentachloride is a yellowish white powder and in moist air it hydrolyzes to POCl3 and finally gets converted to phosphoric acid. When heated, it sublimes but decomposes on stronger heating. Just like trichloride, it also reacts with organic compounds containing hydroxide in them. Are all the 5 bonds in phosphorus pentachloride molecule equivalent? The answer is no. The phosphorus pentachloride has a trigonal bipyramidal structure and the 3 equatorial PCl bonds which are equivalent, while the 2 axial bonds are different and longer than the equatorial bonds. Now, let us talk about oxo acids of phosphorus. All the oxo acids of phosphorus contain one P double bond O and at least one POH bond. The oxo acids in which phosphorus has lower oxidation state, that is less than +5, contain in addition to PO and POH bonds either PP single bond as in hypophosphoric acid, that is H4P, or PH bonds as in hypophosphorus acid, that is H3PO2, but not both, while POH accounts for basicity of oxo acids. These hydrogen atoms which are attached with oxygen in POH, they are ionizable. Now, we can observe the structure and understand why phosphorus acid, that is H3PO3, is dibasic, because it contains 2 POH bonds, and phosphoric acid, that is H3PO4, is tribasic owing to the presence of 3 POH bonds. The pH bonds account for the reducing nature. These pH bonds are not ionizable to give hydrogen ion and do not play any role in basicity. Hypophosphorus acid is a good reducing agent because it contains 2 pH bonds. Hypophosphoric acid, polymetaphosphoric acid and pyrophosphoric acid, none of them have a pH bond, so they cannot act as reducing agent. Hypophosphorus acid, that is H3PO3 is a good reducing agent because it contains 2 pH bonds and reduces, for example, silver nitrate to metallic silver. Acids in +3 oxidation state of phosphorus tend to disproportionate to higher and lower oxidation states. That is why orthophosphorus acid on heating give orthophosphoric acid, in which oxidation state of phosphorus is +5, and phosphine, where oxidation state of phosphorus is -3. Thus, from the discussion we conclude that phosphorus exists in different allotropic forms, out of which white phosphorus is most reactive one. Phosphine is a poisonous gas. White phosphorus forms two types of halides, which are trihalides and pentahalides. Pentahalides of phosphorus are more covalent and two axial bonds are longer and weaker than rest of the three equatorial phosphorus halogen bonds. Different oxo acids of phosphorus exhibit different reducing nature and basicity. Before ending our session, I am giving you some questions to work upon. Question number 1, why phosphine is a weaker base than ammonia? Why are all 5 phosphorus chlorine bonds in phosphorus pentachloride not identical? Question number 3, write name of dibasic oxo acid of phosphorus. Question number 4, which structural feature of oxo acids of phosphorus explain their reducing nature? I hope you have understood the concepts discussed in this episode and you are looking forward to discuss next group of periodic table, that is group 16, oxygen family. But till then, take care.